Okay, in this example, we're going to look at tubes that are being sounded at certain harmonics, and then we're going to look at the temperature dependence of those harmonics. So we have two tubes that are filled with air at a temperature of 20 degrees Celsius. We're told that tube 1 has a length of 1.3 meters and is closed at one end, and it's being sounded at its fifth harmonic. Meanwhile, tube 2 has a length of 1.5 meters, is open at both ends, and is sounded at its third harmonic. What temperature would the air have to be in tube 1 so that these two tubes produce the same frequency? Because if they're both at 20 degrees, they will not create the same frequency. We might as well go ahead and calculate that. Okay. And I've included a formula that we're going to need here for the velocity of sound depending on temperature. And of course, we'll also need the formulas for harmonics. So we'll start with for two open ends. All right, so for tube with two open ends, we have, okay, and we'll refer up to some notes up here where we had a tube that was closed at one end. There we had that L was n over 4 times lambda n. For a tube that's open at both ends, it ends up being lambda equals n over 2 lambda n, okay? And so then down here, for tube with one open and one closed end, L is going to equal n over 4 lambda n, okay? And here we want them to sound at the same frequency, so we can use our relationships with frequency like we did up here. All right, so Fn is nv over 4L for this case, so Fn is nv over 4L, and for the tube with two open ends, Fn is nv over 2L. Okay. So now we want the temperature. Okay, so to be in tube 1 so that the two tubes produce the same frequency. So we're going to vary the temperature in tube 1, but we're going to keep it constant in tube 2. Tube 2 is the one that's open at both ends. Okay? So this one's going to be, just to label them, this is tube 2 here, and this one is tube 1. All right? Okay. So if we want the fifth harmonic, which is or rather in tube 2, we're actually we're interested in the third harmonic. So we're going to have F3. Okay, it's going to be 3 times the velocity. So 331 plus 0.6 times 20 degrees Celsius. And this formula does rely on Celsius. Right, so this temperature right here must be in degrees Celsius. Okay. And then we're just going to be dividing by 2 times the length of the tube, which is given as 1.5 meters. All right, so let's find the fifth harmonic of that tube. Okay, so we have 3 times 331 plus 0.6 times 20. All right. And then divided by 2 times 1.5. All right. Times 1.5, close parentheses. Okay. So we get 343 hertz as the fifth, keep saying fifth, but I mean the third harmonic of our second tube. Okay? All right. So now we want to match that frequency. So for tube 1, we want F5 to equal, because it's still going to be the fifth harmonic. We're not changing the harmonic of that tube or the length of tube 1 or anything. The only thing we're going to change is the temperature of the air inside of it. So we want F5 to equal 343 hertz. At 20 degrees Celsius, it doesn't. Let's just see, right? So note at 20 degrees Celsius, F5 for tube 1 is, that's 5, it would be 5 times 331 plus 0.6 times 20, All right. Okay, and then all divided by 4 times the length, which is 1.3. Okay, so it's pretty similar calculations, so I'll just make some tweaks up here. All right, this would be a 1.3 instead of a 1.5, and it's a 5 instead of a 3 because it's the fifth harmonic. Okay, so that is going to be 660 hertz. So you can see they're really not very close at all, so we're going to need some outrageously large temperature here. All right, but let's go ahead and solve for it. Okay, so then to solve for T needed for tube 1. Okay. We'll set this up otherwise the same, and by this I mean this expression here. The only thing we're going to change is going to be the temperature. We'll leave that as a variable. So I'm going to have 5 times 331 plus 0.6 times T. All right. Divided by 4 times 1.3 meters equals, well, it would not 660, right? But equals 343 instead. Okay. So multiply both sides, do some arithmetic. Okay. So first thing I'll do is multiply by 4 times 1.3 and divide by 5. So let's take this value that we solved for, and we're going to multiply by 4 and 3.1. So 4 times, or 1.3. Okay. Okay. And divide by 5. Okay. So then that's going to give me, I have 331 plus 0.6 times temperature we're trying to solve for equals 357. All right, but I'll keep the unrounded version in my calculator. All right. So then I'm going to have 0.6 T is going to equal 357 minus 331. So it's not an outrageously high temperature. It's going to be a very, very low temperature. Oh, and that makes sense because we're trying to bring the frequency way down from 660 down to 340, and that's going to involve lowering the temperature. The lower the temperature, the lower the frequency. Okay, so we gotta get this tube down to not absolute zero, luckily. So the answer is going to make physical sense, but we're going to need it. We're going to need it low. And actually, to be fair, also these are in Celsius, so really we wouldn't have to worry about breaking the laws of physics unless we got that in the negative 273, because again they're in Celsius. Okay, so let's see. So then I'm going to have T equals, right, so let's take that difference, 357 minus 331. So 357 minus 331. All right, so 25.72, and then we're going to divide that by 0.6. So up here, I'm going to write 25.7 divided by 0.6. Okay, and these are actually in degrees Celsius. All right, so let's take that value and divide it by 0.6. All right, and we get 42.8 degrees. Well, so actually my original statement was closer to the truth, or was the truth. Actually, it does have to be hot. So it has to be 42 degrees. And now it actually makes a pretty significant difference. It's really really changing the pitch by going up. And 42 degrees is actually not an unbelievable temperature. That would just be over 100 degrees Fahrenheit, but not too much above. So there we see the change in frequency of a tube by changing the temperature of the air inside the tube, but not changing any of the properties of it. And in this case, thereby matching it to another frequency. Thank you.